Now that we've been introduced to the antiderivative, let's look at an application. In particular, we'll look at the application that involves an object, a projectile, being launched from the ground well, maybe not from the ground, but from an initial height and an initial velocity. And what we want to do is we want to use the antiderivative to figure out how high that velocity will, what height that object will obtain, how long will it take to obtain that height, when will it hit the ground, and what is the velocity when it does hit the ground. So we want to answer those questions. Now, first of all, some preliminary things we need to think about. We're going to call S of t the height, the distance of the object above the ground. Now, if you think about it, if we want to measure the rate of change of height, that's going to be the velocity. In other words, the derivative of the position is going to be the velocity. It measures the change in position over the change in time. So the velocity is the derivative of position, and then if you want to look at acceleration, well, that's going to be the derivative of velocity, where it measures the rate at which velocity is changing over time. Well, that is acceleration. So that's the first derivative of velocity and the second derivative of position. Now let's suppose, here's the thing to remember. We start off with this number, negative 32 feet per second squared, because that is acceleration on Earth due to gravity. Now we're not going to consider air resistance or anything. We're just going to consider this. This object, when an object is launched, it has this gravity pulling on it. The acceleration is a negative 32 feet per second squared. That acceleration is continuously diminishing from the velocity. So if we launch from a particular velocity, acceleration is constantly pulling on that object, decreasing its velocity. As an example, let's suppose that we launch an object from the ground at 96 feet per second squared. And I'll call that t sub 0. That's the initial velocity. Okay? Now, after 1 second, let's see where the object is. Well, it's traveling, let's see what the velocity is. The velocity is 64 feet per second. Now, look, what's happened here is I took the 96 and subtracted the 32 from it. That's where I got this 64. Because acceleration is decreasing the velocity at this rate, negative 32 feet per second. Every second it's doing that. So the height of the object at that point is 80 feet. So after 1 second, the object is 80 feet. Now, we haven't looked at, you might be wondering, well, how did you get 80 feet? We'll look at that in just a second. But right now, let's just take this as a given. So for the first second, it's traveled 80 feet, and the velocity is now 64 feet per second. Now, I'm going to go to the next second, and because acceleration every second is decreasing the velocity by 32 feet per second, this next one should be 32 feet per second. See, I took 64 minus 32, and now the height is over here at 128 feet. But you notice, if you go back and look at this, during the first second, the distance the object traveled was more than the second. See that? The second? Look at the little ball, how it travels. Now the third second, it's going to travel even less distance because it's going at a less velocity. So after 3 seconds, notice I'm going to subtract 32 from this. The velocity will be 0. Notice it just travels a wee little bit there. Notice from here, whoops. Okay, just a little bit. See that? Just a little bit up there. Now, the velocity is 0, and we are at the very top, 144 feet. Now, after 4 seconds, it starts back down. Now it's back to 128. It's back to 80. And notice now the velocity is negative. When our distance was increasing, the derivative was positive, right? When the distance from the ground is decreasing, our velocity is negative. See, we're falling. Negative 32, negative 64. Now I subtract another 32 from it and back down on the ground. And it looks like what happened was it took this thing 6 seconds to go from the ground to reach its maximum height and then be back down. Now this is a graph of the function. And this right here models the up and down movement of the ball.
So now let's look at the calculus involved in that problem. We said that the initial velocity was 96 feet per second. Okay, so we've got that. And notice I just denote that with v sub 0. And of course the acceleration was a constant negative 32 feet per second squared. Now, here's the deal. The derivative of velocity is acceleration. So acceleration measures the change in velocity. So the difference in velocity over the change in velocity over change in time. That's what we're talking about when we talk about acceleration. So what I need to do then is, if I start off with acceleration, I need to get back to velocity. So I integrate that. So velocity is going to be the indefinite integral of negative 32. And that gives us v of t is equal to negative 32t. Plus, remember there's a constant. Now, in this case, we can actually figure out what that constant is because we know the initial velocity is 96. So if we say, well, let's put in a 0 for time, because at time 0 we had a 96 velocity. So this is equal to 96, and I'll leave off the units here. That means that 96, when we put in a v of 0 here, we get negative 32 times 0 plus c, and we see here that c is equal to 96. So now here's what we've got. We've got our velocity, which is negative 32t plus 96. See, just putting the 96 in place of the constant. Now, this thing slows down as it gets further from the ground. And remember, we said that it reaches its maximum height after 3 seconds. Now, think back and remember, when we were finding high points on curves, what we would do is we would take the derivative and set it equal to 0 and get our critical numbers. Well, that's kind of what we're going to do here, because we've got the velocity, which is the derivative of the previous function. Well, the previous function was position, the height of the ball, the distance of the ball above the ground. So if we take the derivative of position, that is velocity. The change in position over time, that's velocity. So if we take the derivative of position, we get velocity, and of course I set this equal to 0. So I've got negative 32t plus 96 equals 0. Now, of course, you don't have to think through it the way I just did. You're just saying, we know that when the ball reaches its highest point, it kind of stops. The velocity is 0, and then it starts heading back down. So just figure out where the velocity is 0. A little algebra gives us t equals 3. So that's where it reaches its highest point. Now we want a formula for the position. Well, I already said the derivative of position is velocity, so now I integrate velocity to get position. Okay, so this is going to be the integral of negative 32t plus 96. And when we go through this, using the power rule for integration, we get negative 16t squared plus 96t plus another constant. Now this time, the initial height, we launched this ball from the ground. So since we launched this ball from the ground, we know that s of 0 is equal to 0. So the constant is equal to 0. See? Because if we put a 0 in for t and a 0 over here for s of t, we just get c1 equals 0. So now here is our function for position of the ball. It's negative 16t squared plus 96t. And now, let's suppose we want to say, well, when is that ball going to hit the ground? Well, that ball is going to hit the ground whenever 16t squared plus 96t equals 0. And we can solve that, by one way we can do it is just by factoring. We can factor out the t, and actually I could factor out the 16, negative 16, so I get negative 16t, and let's see here, this would be t minus 6, right? And that means that the ball is on the ground at t equals 0 or t equals 6. And we could say, well, what is the velocity when the ball hits the ground? Well, if you want to know the velocity when the ball hits the ground, just take this 6 and plug it back into the velocity function here. So v of 6 is equal to negative 32 times 6 plus 96. And I guess that will give you negative 96 feet per second. There you have it. Okay, now let's suppose, let's make the problem a little more complicated. Let's suppose that the initial velocity is 128 feet per second. Okay, 128 feet per second. And let's suppose that the initial height of the object, I guess we've been calling it S. The initial height of the object is 10 feet. Let's suppose we have that. Okay, so we still proceed the same way because our acceleration is still negative 32 feet per second squared. So here's what we do. We integrate this, and we get that the velocity is negative 32t plus a constant. Now, if you think about it, that constant is just going to be the initial velocity every time, because what we do is we put the initial velocity over here, a 0 in for t, and yeah, this constant is going to be the initial velocity. So what we have is we have v of t is equal to negative 32t plus 128. That is the formula for velocity. Now here's what question we can answer. When will the object, the projectile, reach its maximum height? Well, whenever this velocity is 0. So to answer that question, when will the projectile reach its maximum height? Well, set the velocity equal to 0, and when you do, you get t equals 4. So we know that after 4 seconds, this projectile will reach its maximum height. It's pretty cool we can figure this, We can use our calculus to calculate, cool stuff like this. Now, let's suppose we want to know, well, what is that maximum height? Well, we need to integrate velocity. So we get the position is going to be, using the power rule for integration, we get negative 16t squared plus 128t plus the initial height. Well, the initial height was 10 feet. So we got negative 16t squared plus 128t plus 10. Now, we want to know, well, what is that height going to be where it reaches its maximum at t equals 4? So I just plug in a 4 every place I have a t, and I get 266. So 266 feet, that's how high this object reaches. Now, maybe we want to know, when does the projectile hit the ground? How long does it take the projectile to hit the ground? Well, we need to take the position function, negative 16t squared plus 128t plus 10, and we just set that equal to 0. And of course, I can use the quadratic formula for that. So I've got t equals negative 128. And use minus. Remember, it's plus or minus. If you use a plus, what you're going to get is a negative number, like negative 0.07. So let's just use the negative. I've already tried this in advance, so I wouldn't waste your time. So we have b squared minus 4ac, but that's going to be plus because we've got a minus there in front of the a. Okay, so we've got 4 times 16 times 10 all over a negative 32. See, it's 2a. And when we work this out, we get t is equal to 8.077. That is how long it takes from the launch of the projectile until it hits the ground. Now, if you want the velocity at that point, in other words, what is the velocity of the object going to be when it hits the ground? Well, I just plug that in. And I get the velocity when it hits the ground.